Hello and welcome to another video. Today we're going to be doing chapter 13.6. It's going to be a little bit of a long one. I wanted to integrate some theory before we get to the Pearson question, and as well this is all going to be coming together. It's going to be an Excel tutorial. It's going to be some theory and directly on a Pearson question. So hopefully by the end, heteroscedasticity, not so hard for you to understand. It's usually one of the sections that tend to trip students up and give them a hard time on the exam. So let's get this covered so you don't have any problems. So what is heteroscedasticity? Essentially, we're building these linear relationships by using least square estimators, right? Essentially, we're building a linear relationship that is the minimal distance between all the error terms, right? It minimizes the distance between all the terms collectively. And so we have these variances, right, between the error terms, and usually we want them to stay constant. You can see the lower graph, it's a little bit cut off, but you'll get the gist. We want the error terms to remain constant as it goes along, like constant fluctuation. When we have a heteroscedastic result, as you can see in the top, the error terms will get further and further apart as the regression goes along. And so what does this mean? This means that the result is becoming less reliable as the regression continues, and also that there's probably some omitted variable that's causing the regression to get wider and wider as it goes along, right? There's an influence there that's not being reported, and we can see that because the variances are going farther apart, and the results becoming less reliable, but there is some indication of a relationship, but then something goes awry and the results get skewed. So there's definitely some factor that we're not including that's having an effect on our relationship. Okay, so that's how you usually are going to do a heteroscedastic check, by analyzing the residuals versus the x variables. Okay, and we are going to end up doing a chi distribution test using n times the correlation coefficient of the residual plot of the residual to x, and we are going to plot that. That is the residual squared in relationship to y, in relationship to the predicted, and we are going to use that against a chi with 1 degree of freedom. And this is a little complicated, but I'll show you when we get to the question. So just hold that in mind, that this is what we need to do the test. Next, our fix. Oh, a little cut off there. Let me bring it down. This is our fix. It's the formula we use to correct for heteroscedasticity. Don't worry too much about how it works. What's more important is that you have this memorized. This is a question that comes up on the exam. It'll ask you what the formula is, but they won't ask you. The exam is usually all multiple choice for as long as I've known. So they will not ask you most likely to calculate this. So let's hop into our Pearson question. So we have our data set here, which is family income against price, house price being our dependent variable, and family income being our independent variable. Okay, we have our chi distribution table here, where we'll look at and we'll find our critical threshold when the time comes. And so what you want to do is grab your data set, house price and family income, and you want to open that in Excel, as we always do. And so let's get over to that. So here we have our Excel graph, and let me just bring this down a little bit. There you go. So let's start by getting our regression, because it's the first question they want. They want us to estimate the regression with house price being the dependent variable. So we can just do that quickly before we start this problem. So we have our y input being house price in this case, and our x input range. And sometimes they'll put the y first in the data set or the y second, and don't always assume. Usually the way I used to do it was I always assumed the y was first, and I would always get confused after why my regression wasn't right. But sometimes they'll put their x variable first, so just pay attention to that. We're going to include our labels. The constant is not 0. Anyways, and we'll put it to come out to a new sheet. And we'll also have a residual plot, which we'll get to analyze. We'll get to see the heteroscedastic component to this data set. So let's go ahead and do that. All right, so I can pull that up now. So here we go. Here are the plots against family income. And you can already see the way the residuals are getting further and further apart as the regression continues, right? As the x intervals increase. And so this is right away one of the first ways you're going to go and check for heteroscedasticity. And so this is very obvious. We can see that the variances are increasing as x continues. So let's answer our first question to start this off. I believe they want 2 decimal places, so let's go ahead and round these down to 2. Perfect. And we'll just copy paste that. And we'll copy paste that. So let's go ahead and check it. Awesome. All right, so now it's asking us to check for heteroscedasticity graphically. So as long as you tick those boxes off, all the ones I had ticked at the beginning, you can, you'll get to see it graphically displayed here. And that'll be the easiest way to do it. So obviously it only matches up with this one, so we can continue. Great. So yes, like I explained before, there is evidence of heteroscedasticity because the variances of the error terms are getting further and further. Now we're going to determine our chi-squared critical value. And it's always going to be with 1 degree of freedom, alpha. So what that means is, if I can find the alpha here, I must be blind. Oh, it's down here. 5% significance. Great. So always when you're doing a heteroscedasticity, well, that is going to be tough for me to say. A heteroscedasticity test, you're going to want to open your chi distribution values, and it is going to be 1 degree of freedom when whatever the significance level is. So 3.841. It's as simple as that. It'll always be chi squared, 1 degree of freedom, and alpha. So it's as simple as looking at the first row on whatever the alpha is. So we have 3.841. 3.841. Awesome. Now we're going to calculate the test statistic. Okay, so when we're doing the test statistic, we actually aren't going to use this R. This is the wrong R. You have to plot the residual squared, okay, against the predicted house prices, using the residuals as Y and the predicted house prices as X. So let's just get that here. We'll call this residual squared. And we'll have this cell equal the first residual cell squared. And there's about 30 observations. So let's just go down and it'll end right there. So that's 57 to 87. That's 30. Awesome. And then we're going to have our predicted Y. And we'll equal that to the predicted, which is conveniently given to us. Make sure you click all the boxes that I said so you can get this type of statistic, the residual outputs here. And then we are going to do it again. We're going to go, I won't bring it down to show you, won't fit in the screen, but we're going to go data and back to data analysis, and we're going to redo another regression. And on our new data set, having residual squared as Y and the predicted Y as X. Great. And we are going to go OK. Oh, I didn't change the names, so it'll give me just a generic sheet 1 name, but that's okay. So we'll have new plots. And we're going to be using this R. Okay, so now to do our statistic, we're going to go with this, the R squared, sorry, not the multiple R, the R squared times the observation, so n times r, and that's going to give us 7.5318. And how many decimals? 3 decimals. So let's round that down to 3. And plug it in, and hopefully we did that right. Great. So since our test statistic is greater than chi-squared, we are going to reject the null that there is no heteroscedasticity. So which one would that be? Since the test statistic is not greater, no, is greater, reject HO, that the error terms have constant variance. Exactly. So since the test statistic is greater, so 7.532 is greater than 3.841, okay, we're going to reject HO, that we believe that the error terms have constant variance. In other words, no heteroscedasticity. But as we've seen, obviously here, I mean, it didn't really take the test to figure that out, but we know that it does, in fact, display heteroscedasticity, and the test just confirmed that there's evidence to suggest that there is. Okay, so let's go ahead and do that. Great. So now we're going to fix it. We're going to create a new linear correlation. And you don't have to read too much into it. There won't be, as far as I remember, there were no theory questions on what this means, and the book doesn't go into great detail about explaining how this really addresses heteroscedasticity. So I wouldn't put that on the forefront of what you need to absolutely need to memorize. I mean, if you have a minute, maybe talk to your teacher and have him explain it to you. So let's go ahead and fix the regression now. So we're going to click on this, but we're going to get back to this and we're going to fix it on our Excel first of all. So this is the the predicted value of y, okay? So let's go to our predicted value of y, not from this, from our original regression. Now let's name this data sheet so we're a little more organized, and we can name this regression residual, so we're not confused. So let's go back to our original regression here and take our predicted y's, okay, and we'll bring it to our data sheet. And we'll just put that in. Oh, yeah, you see, you might want to paste special and only keep value and number formatting. That way we keep all our numbers, and or else we're taking down the formula, and that's why it's not corresponding. So we have our predicted y, so let's get started. So the first part of this formula, as you can see here, is y, the y results that we obtained over the y expected, okay? So it's as easy as going, usually I'll just write it out just so I can have it. So I'll go y over y expected, okay? And we'll have, I believe y was house price, if I'm correct. Yeah, so our dependent variable was house price, so we'll do this over predicted y, and it's as easy as that, and we'll pull it all the way down. And so we have the first part of our regression, okay? And then the second part is going to be 1 over y expected, so we'll have that here, 1 over y expected. Okay, as simple as doing 1 over, again, predicted y, and I forgot to put the equal sign here, here we go. Right, and then we'll drag it down. All right, and the last piece is x over y expected. And you can probably figure it out by now. Family income is y, so x, so we're going to divide that by y, predicted y expected. And then drag it down. And this is what we're going to use to build our last regression. So for the last time, to get our fixed solution for the regression that corrects for heteroscedasticity, we're going to go to data analysis, regression. Okay, now this is the important part for this step. Okay, we can keep the labels, that's fine. It'll be easier to look when we get our new regression. We're going to highlight 1 over y expected and x over y expected as our x variables. Okay, and our constant in this case is going to be 0. Okay, it's not going to work if you don't take this. You're only ever going to use this feature. Okay, don't need to know why, or maybe ask your teacher why, because I don't think I know the reason, to be honest. This part I'm not. I know how to do it, but it's there are some theoretical details that are missing. So if you want further clarity on the subject on this specific topic with this formula specifically, you're better off asking your teacher. So yeah, so we'll have these as our x variables, and our y over y expected as our dependent variable. A constant will be 0, and we'll have our labels included or not. It's whatever you prefer. And we'll have this pop out to regression 3 on a new worksheet. And there you go. And let's see how many decimals. Round to 2 decimals. So no coefficient. Let us round these down to 2. There you go. And we'll just drop those in there. And hopefully I don't have to restart this video. That's great. So that's it. That's heteroscedasticity for you. Theory is more important, I would say, in this section than the math. You want to know, especially for the exam, what you want to know are the signs for heteroscedasticity. They will most likely ask you multiple questions on this topic. As we said before, usually, right, the sign is that we'll see the variance getting wider, and the main cause for this is usually that it could be many things, but a lot of the times it'll be an omitted variable that's having a significant effect on the relationship. So that's it. We'll get back with chapter 13. We'll continue on until we have all of Econ done. But for now, thanks for watching, and I'll see you in another video.